All right, good morning, everybody. So now let's start. Let me just recall what we did last time. So I guess last time we were talking about the alternating series test and test for absolute convergence. So we said that there are two steps for the alternating series test. First, you need to take a look at the limit of the positive factor, right? So in this case, just to clarify, you will be given an alternating series that is characterized by a factor that causes the series to alternate between a positive term and a negative term, right? So that's what this factor does. It could be -1 to the power n plus 1 or -1 to the power n plus 3. All you need to check is that that causes the alternating sign, right? And in this set of notes, I guess I used the notation a sub n to denote the non-alternating factor, right? So in this case, a sub n doesn't change sign; it's always positive, and that's what we will analyze for the alternating series test. So you ignore the alternating factor, check if the ANs would be decreasing or eventually decreasing. That's a more general statement of the alternating series test, and take the limit of AN. And if it's equal to 0, then the series is convergent. So if it happens that the limit is not equal to 0, then you can conclude that the limit of the entire term will not exist. And so by the basic divergence test, the alternating series will be divergent. So that's the nice thing about the AST, because the crucial part here is condition number 2. So we often start with condition number 2. If the limit is equal to 0, then proceed to test condition 1, right? But if condition 2 is not satisfied, then the series is automatically divergent via the basic divergence test. All right. Oh, hold on. I think I'm on the wrong worksheet. So that's for my other lab. But let's see. So I guess last time we spent a lot of time doing some exercises on the ratio and the root test. So we were only able to cover, I think, 3 examples. So let me see. There are some questions in the chat, and I'll be happy to answer them if they are about alternating series. Oh, Taylor sent a nice question here. Let me see. Okay, let me flash the question here. How can I do that? Okay, let me see here. All right, so yeah, um, there are probably a couple of or 3 students asking me this time during my this problem during my tutorials. But let's see. So here f is a continuous, positive, and decreasing function, so it fits the category for the integral test, right? And fn is equal to an. If this guy is convergent and it has some L, which of the following must be true? So all the problem is telling us is that the sum of an and from 1 to infinity is equal to L. Okay, so that's what this is saying. But let's check which of the following is true. Well, this guy will be false, right? So why will this be false? Because you should remember that if the sum of AM is convergent, then automatically the limit of AN as n approaches infinity is equal to 0. This is basically the foundation of the basic divergence test. This is the converse, which is an equivalent statement to it. So if you already know that the series is convergent, then automatically the limit of an should be equal to 0. So option D is wrong unless L is equal to 0. But we don't know if L is equal to 0, so I'll say this guy is wrong. Okay. Now, If you look again at the problem, the function f satisfies all the requirements of the integral test, right? So the integral test tells us that if the improper integral converges if and only if the series converges. Okay, so that's the only thing that the integral test will tell us, right? So that means from that basic statement, this should be wrong because we already know that the series is convergent. So that means the improper integral should also converge. So the improper integral cannot be infinite. Okay. Now you're down to options A and C, but here's the thing: the series and the improper integral are not necessarily equal to each other. Okay, so that means you cannot say for certain that C is true. It can be true, but it can also be false. We don't know. We need more information about F and A. So which leaves us to option A, which is also the safe choice because here we're saying that if the improper integral converges if and only if the series converges. So what does convergence of an improper integral mean? It means that the improper integral has a finite value. So we already know that the series is convergent. So that means the improper integral must be finite. All right. I hope
Why
that
does
that
D
you're.
not work again?
Oh, sorry.
Why does D not work? Why can't we do D? Why does D not work?
Oh, they will not work because of this fact over here. Okay. So if the series is convergent, then automatically the limit of the n term a sub n is equal to 0. That is a necessary condition, which is equivalent to the basic divergence test, right? Remember that the basic divergence test tells us that if the limit of an is not equal to 0, then that means the series is divergent, right? But if L is not equal to 0, then that will make the series divergent. But we knew from the assumption that the series is convergent. All right. Does that make sense?
Yeah, that makes sense.
Right. So yeah, just a couple of things here. If an, just to drive the point, if the series converges to L, then these two things are true. First, the limit of an as n approaches infinity must be equal to 0 because if it is not equal to 0, then the series should diverge by the basic test for divergence, right? So necessarily the limit of an must be equal to 0. And another fact is the limit of the partial sums as n approaches infinity is equal to L. So sometimes students confuse the limit of the n term and the limit of the partial sum, right? So if the series converges to L, the n term, the thing inside your summation, will have limit 0, but the partial sums will have limit L. Okay, I think there's an analogous question like that in the quiz that the electronic homework or the electronic quiz. So hopefully that clears things up. Let me see. There's another question in the chat. I see that Morel and Herson are discussing things over here. Let's see. Let me go to Herson's question. Were you able to resolve Herson's question in the chat? If not, then I can try to answer this. What is the this question? Okay. So what's the instruction here, Herson? I'm guessing this is to check whether it's absolutely convergent. Okay. So just a quick recap. We say that a series AN is absolutely convergent if the series with the absolute value is convergent, right? So series AN is absolutely convergent if the series with the absolute value is convergent. And there's a nice result if AN is absolutely convergent, then it is also convergent. All right. Why does it follow that it is also convergent? It is because if it's absolutely convergent, then the series with the absolute value is convergent. But this series is larger than this series, right? So we have this relation. So this series is smaller than a convergent series. By direct comparison test, this guy must also be convergent, right? That's why sometimes you will see in some textbooks the ratio test and the root test are done with absolute values, because it follows that if the series is convergent, is absolutely convergent, then it will also be convergent. Now we say that the series AN is conditionally convergent if it is convergent, but the series with the absolute value is divergent. So I know that you were given a lot of problems to check whether a given series is absolutely convergent, conditionally convergent, or divergent. So these are the definitions of those guys. And so let's go to Herson's question to exemplify these concepts here. So we are dealing with the sum of negative 1 to the power n over ln of n plus 10 and going from 2 to positive infinity. All right. So here, what I usually do is to take the limit of try to see if the one with the absolute value is what I usually do is to take the limit of the positive term, because that will be a two-pronged solution, because here I'll try to take the limit of 1 over ln of n plus 10 as n approaches infinity. Why do I say that this is a true two-pronged solution? Because this is the setup for the alternating series test, right? Which will tell me if this series is convergent, right? So this is essentially the setup for the AST. Take the limit of the positive factor as n approaches infinity. If it's equal to 0, then proceed to the next step of checking if this guy is decreasing, right? Now, if this is equal to 0, I can proceed with AST. If this is not equal to 0, then I can conclude that it would be divergent. So there would be no questions asked. Also, this is also a setup for the basic divergence test for the series with the absolute value. So starting with this is advantageous in several respects, because this will give you some ideas of what are the conclusions that you can make out of this single limit, right? Either AST or BDT. But let's see. So here's that's my approach here. But obviously this will be equal to 0, right? Because when n becomes large, n plus 10 becomes large, ln of a large number is a humongous number. So 1 divided by a large number, that will go to 0. So that means there's a chance that alternating series test will apply here. Now, note that AN is equal to 1 over ln of n plus 10, which is obviously decreasing. It is obviously decreasing because when n becomes larger, n plus 10 is larger, ln of n plus 10 would be larger. 1 divided by a larger number would be a smaller fraction. So I know that this will be decreasing. So by AST, the given series with the alternating sign is convergent. But this still has two possibilities. Either this series is conditionally convergent or absolutely convergent. So now let's test for absolute convergence. So how do we test for absolute convergence? So we consider the series with the absolute values. So enclose everything inside an absolute value, right? And see if this is convergent. If this is convergent, then the series, the given series, is absolutely convergent. If this will diverge, then we have a conditionally convergent series. Okay. Now, what's the effect of the absolute value bars? The top factor will just be gone. Okay. So, and then this is what we want to test. So you can do any of the tests that you can remember, but I guess I can do a direct comparison test here. Compare it with the sum of 1 over n plus 10. All right. LNs are smaller than n. Sorry, an ln is smaller than its argument, at least eventually. So this guy would be smaller. Sorry, this guy will be larger. So I'm making the whole fraction smaller. All right. Again, the denominator here is larger because it is out of the ln. So this guy is larger. So that means the the fraction is smaller. So that means we have that relation. All right. Now, actually, I can further simplify this as 1 over n. So again, what I did here is to lower down the denominator, and that makes the fraction larger. Or probably I should not do that because I will have this inequality here. But essentially what I can say here is, what can you say about this guy? This is, this series differs only by a finite number of terms. With the harmonic series. And remember, if a given series differs only by a finite number of terms from a given series, then they will both converge or they will both diverge, right? So this guy looks like the harmonic series. It's just that it starts at 12, right? It starts at 1 over 12. But the harmonic series starts at 1, then 1/2, 1/3, and so on. But they will only differ with the first 12 terms, right? First 12 or first 13 terms. So, but the point is they will differ only by a finite number of terms, so they will have the same behavior, right? But it's a harmonic series, so that's divergent. So this guy will be divergent. So the series on the right is divergent. You could have also used the limit comparison test for this guy. You will see that the limit will be constant if you compare it with the harmonic series. So that means they will both diverge, right? So this is divergent, but our given series is larger than that divergent series. So that means that by direct comparison test, this series, the series with the absolute value, is divergent. Right? Therefore, the original series that we were given is conditionally convergent. Because on itself, it is convergent, but with the absolute value bars, it becomes divergent. I see Morel and Hersen has the same idea for the solution. Okay, so 1 over n is divergent because it's the harmonic series. Okay, does that make sense?
Hey Neil, I have one question.
Go ahead.
So about the one that we compared the 1 over ln of n plus 10 to, so I'm not understanding how it's divergent.
Okay, yeah. So this, but I hope you see the you see the point why I am comparing this guy with this one, right? How I
Yes.
got this less than this inequality here. Now, I'm dealing with this guy, 1 over n plus 10. There are several ways on how to conclude that that is divergent. I guess that's your question. For me, the easiest reasoning why this would be divergent, because it looks like the harmonic series, right? Remember the harmonic series? The harmonic series is sum of 1 over n, starting from 1 until infinity, 1 over n, right? But the harmonic series is 1 plus 1 half plus 1 third plus 1 fourth plus and so on, right? Plus 1 over 12 plus 1 over 13 plus 1 over 14 plus and so on. That's the harmonic series once expanded, right? Good. Now,
Yes.
if you look at the series that I'm comparing the given one to, so this guy, it's 1 over n plus 10, starting from n equals 2. So basically, it will have the same pattern as the harmonic series, right? Because
Oh,
the first term here is 1 over 12, followed by 1 over 13, followed by 1 over 14, followed by 1 over 15, and so on. So essentially, this is the harmonic series, except it starts at 1 over 12.
okay.
So it then start here. The thing is, if that happens, if your series will only differ by only a finite number of terms, in this case, we only differ by 12 terms to the harmonic series, then they will still have the same behavior. Because since the harmonic series is infinite, this guy will be infinite because you are just subtracting a finite number of terms.
Okay, that makes
Uh,
sense. Thank you.
Right. If you're not convinced with that, or you cannot think about it that way, you can do limit comparison test here with the harmonic series. And you will also come up with the same conclusion, right?
Thank you.
Sure. What if it was n squared plus 10 instead of n plus 10? Hersen, if it was an n squared plus 10 in the denominator, then you'll do limit comparison test with the p series 1 over n squared. And you will see that that will be convergent, right? Because 1 over n squared plus 10 will behave in a proportional way to 1 over n squared. So by limit comparison test, if you take the limit of the ratios, it will just be equal to 1, which is finite. So that means they will both converge, because 1 over n squared is a convergent p series because p is equal to 2. But your direct comparison test here will fail because you have a smaller convergent series. LCT won't apply, right? So perhaps you'll need a different test to conclude the convergence or divergence of this one. All right. Okay. The next question in the chat is from Morel. Were you able to clear this up per your conversation with Herson in the chat?
I kind of would like an example of it, please.
Oh, sure, yeah. You mean answer the question you sent or a different example?
Well, answer it, please, because I have a few that are similar to it. So.
Sure, no worries, yeah.
Thank you.
Let me see. Problem 10. Okay, problem 2. Same question. Okay, absolutely convergent, convergent, or divergent. So you have the series -1 to the power n of n to the 11th plus n. I'm thinking there should be a grouping symbol over here. Over n to the 12th plus 5n to the 4th plus 3. And going from 1 to infinity. Okay, there would be some issues if there were no grouping symbols there. So I'll insert them, and I guess that's the essence of the problem. So again, for testing for absolute convergence, I always start with taking the limit of the positive factor. Again, this is a dual-pronged approach because if the limit happens to be 0, then I can proceed with the alternating series test. If the limit is not equal to 0, then the series with the absolute value will become divergent. So yeah, you can conclude some things about that. So let's see. Okay, now the degree of the top is 11. Degree of the denominator is 12. Denominator wins by Bobo. The limit is equal to 0. So we can proceed with the alternating series test. For the alternating series test, we want to show that this guy is decreasing, or at least eventually decreasing. Now, how do we show that this is decreasing? This is the thing about complicated polynomials over complicated polynomials. When n becomes larger, the numerator increases, and assuming that the denominator remains the same, then the fraction would have increased. But the denominator is also increasing, right? So if in a fraction the numerator remains the same and denominator is increasing, then the entire fraction will be decreasing. So the thing here is both increases, so we don't know which wins. Will it be increasing or decreasing, because the top and then the denominator has two different behavior, right? Now, there are several ways on how to do it. You can take a look at the ratio between a sub n plus 1 all over a sub n and check if it is greater than or less than 1. Or as Maria is suggesting, you can check a sub n plus 1 minus an and compare it with 0, right? Do you think it would be yeah, that's one thing about this guy. What would be easier, the ratio or the difference? Come again?
Will you use the root test for this?
I'm not using the root test yet because here I am proceeding with AST. So what I want to show that this guy would be decreasing.
Couldn't you plug in 1 for n, and then like as it approaches infinity, we already know that it approaches 0. So if that first number is positive and it approaches 0, we know that it has to eventually be decreasing, right?
That's a good point. But the thing is, I want to avoid oscillation in behaviors, because you can still have a small number. Say you get 1 for the first term, then you get 0.5, then you get 1, then you get 0.75, then you get 0.77. But the thing is, it should be decreasing all throughout. So there could be an oscillation in behavior. They can eventually oscillate to 0, but the AST is quite strict, because you don't want an oscillating behavior between the terms. So yeah, we need to be strict and work this out nicely to show that this is decreasing. A sub n plus 1 over a sub n, or a sub n plus 1 minus a sub n, I think will complicate things up, because whenever involving a sub n plus 1, we should replace all n's by n plus 1, and they are inside powers. So that's why I'm thinking perhaps looking at the derivative would be much easier here. Because remember that if the derivative is positive, it would be increasing. If the derivative is negative, it is decreasing. So let me try this one. See if this will give us a nice answer. And that's my worry about this problem, because you have large exponents. So the expansions might not look good. But let's see if this will lead us somewhere. If this is my f of x, then f prime of x will be obtained by using the quotient rule. So it's low derivative of the high, which is 11x to the 10th plus 1 minus high derivative of the low x cubed, right? And let's see. What happens here in the long run? Well, the denominator is always positive. So all we need to look at would be the behavior of the numerator, right? So in the numerator, what do we get? So in the first, in the minuend, we get what? The leading term here would be 11x to the 22nd power, right? When you carry out the multiplication with the highest power. So we'll get 11x to the 22nd. While on the subtrahend, we'll have 12x to the 22nd, right? And the lower order terms will not matter, because that means that in the long run, they will be insignificant, right? So all that matters would be the largest powers. So the largest powers would be the 22nd powers. The minuend has 11x to the 22nd. The subtrahend has 12 to the has 12 times x to the 22nd. So that means this will eventually be less than 0. And this this verifies the suggestion earlier. I forgot from whom it was, saying that this will eventually be decreasing. So I just need to wrap my head around that statement and prove it for a fact, right? So for sufficiently large x's. So ANs is eventually decreasing. Now I'm convinced. So with that statement, so the series, the alternating series is convergent. So there's a distinction here. What we have shown is that the given series with the alternating sign is convergent. Well, Herson, the denominator, yeah, there would be a higher, yeah, the denominator will grow faster, but essentially this will go down to 0. But again, we need to make sure that this is decreasing, because that's only one part of the AST. What you're saying there, Herson and Maria, what you are saying is actually covered by the first statement, that the limit will be equal to 0. All right. So that's the first part, but that is insufficient to conclude that the series is convergent, because this doesn't necessarily imply that the series is the terms would be decreasing. They will eventually go to 0, but we don't know if they will really be decreasing, because what we are avoiding is that they might be going to 0, but they are not decreasing. Because one behavior that we are avoiding is this: you could have a 1 followed by, say, 0.5, then followed by 0.75. Oops, maybe I should phrase it in terms of alternating signs. So from here to here, it decreased, but from here to till there, it increased. And then say what happens next is you have a minus 0.25, and then plus 3.7, plus 0.375 minus 0.125 plus 0.25, right? So this patterns, the terms will go to 0, right? Because essentially they will decrease, okay? But the thing is that it is not decreasing, because there are some times that it will increase, sometimes it will decrease. So though the terms will approach 0, but it is not eventually decreasing, because there are terms when it will be increasing or not. In such cases, the alternating series test will not apply. All right. So that's why you really need to make sure that this is decreasing, and you need to say something more than just saying that the denominator will be increasing at a faster rate. Because the thing here is that we don't know what happens in fractions. So you should be more careful, because there's a threshold on how fast the denominator must be increasing faster than the numerator to get a decreasing behavior. All right. So at least here, if that's the case, then we have shown that the series is that the given series is convergent. So the next is to test if it's absolutely convergent. Yeah, that's one drawback of the alternating series test, showing that the ANs would be eventually decreasing might require some work, right? Because that's an important step. The limit the limit being equal to 0 is not necessary, or is not sufficient to conclude convergence. Now, to test for absolute convergence, because unfortunately for us, the given series is convergent, then it can still be conditionally convergent or absolutely convergent. So we need to test this series, n to the 11 plus n over n to the 12 plus 5n to the 4th plus 3. So n goes from 1 to infinity. And here I will use limit comparison test. Because I can design a series that will behave exactly in the limit proportional to this one. So if I'm using LCT, so we note that we can consider this testing series, right? I know that in the long run, the numerator will just behave like n to the 11th. And the denominator in the long run will just behave like n to the 12th. So that would be my testing series for the LCT. So for the limit comparison test, you can just take a look at your series and see how it behaves in the long run. And we'll take the limit against that testing series, right? So again, when n becomes very large, the n on top becomes insignificant. So the numerator just behaves like n to the 11th. In the denominator, 5n to the 4th plus 3 becomes insignificant when n is very large. So that means n to the 12th, the denominator behaves like n to the 12th. But you can simplify this as 1 over n, which is the harmonic series, which is divergent, right? So I know now here, or I have an idea that this will be divergent, right? And to verify that, you take the limit of the terms in your series. Remember the limit comparison test. You take the n term in your given series over the term in your testing series. My testing series I know is the harmonic series. And take the limit as n approaches infinity. Then when you simplify, this will just be the limit of n to the 12th plus n squared all over n to the 12th plus 5n to the 4th plus 3. as n approaches infinity. They have the same degrees, so that means that the limit will just be the ratio of the coefficients of n to the 12th. So this is equal to 1, which is finite. So the given series which is basically the series with the absolute values, is divergent. So the series with the alternating signs is conditionally convergent. Because on itself, it is convergent, but the ones with the absolute value is divergent. All right. Is that good?
Yes, thank you.
All right. Let me see. Herson. I think here you're talking about convergence of that series. Let's see. This is problem 3. There are several ways on how to work this out, but let's see. Ln n over n squared. I'll try first comparing it with 1 over n squared. And what's the relation? Is it smaller or larger? Well, what I did here is to make the numerator smaller, right? Because supposedly have ln n. The smallest value here. Should I cheat a bit here? Yeah, perhaps I'll cheat a little bit here. I'll start at 3. But essentially, this will just differ with your given series by only the first term, so they will both converge or diverge. So what I did here is to lower down the numerator, copying the denominator, so that made the fraction larger. So that means, I decreased the numerator, so I decreased the entire fraction. So that means this guy will have this property. All right. But this is what? This is convergent. My series is larger than a convergent series, then this is not the right the right comparison. So let's try again. What happens when I compare it with, I'll replace the top by n. What I did here is to increase the numerator. If I increase the numerator, I'm increasing the entire fraction, right? So that means this is larger, but this is divergent because this is the harmonic series. My given series is smaller than a divergent series. No conclusions can be made, unfortunately. So what can I do here? Because I know here that basic divergence test will not apply because the numerator grows slower than the denominator. So that means this limit will be equal to 0. What would be the easiest test here? Perhaps I can use the integral test, but that would be my last resort.
What about the P series? Can that work?
Yeah, that's what I'm trying. That's the first thing I tried, Morel, what you're suggesting on the chat. If I compare it with 1 over n squared, okay? And this guy is convergent. You mean limit comparison test? Because direct comparison test will lead me nowhere. Because what I have here is that the given series is larger than a convergent series. Direct comparison test won't apply. But let me see, perhaps you're referring to a limit comparison test? But actually it won't limit comparison test won't apply because here I'll take the limit of ln n over n squared over 1 over n squared as n approaches infinity. Now, this will simplify to limit of ln n as n approaches infinity. Then this will be equal to infinity. So limit comparison test won't apply here. Actually, that's what I'm avoiding. I'm avoiding using the integral test. So that's why I'm exhausting all the tests that we can apply here. What do you think, guys? What are the other tests at our disposal? The ratio test? Well, if we do the ratio test, we'll be taking the limit of ln of n plus 1 all over n plus 1 squared all over ln n over n squared as n approaches infinity. Well, Maria, it's not always the case. If you have ln's in the numerator, some other test might still apply. But for me, that screams integral test. It's just that all the tests that we used here, the comparison, limit comparison tests, didn't work out well. So that means, yeah, I'm reserving the integral test as last resort. But other tests might apply to ln, not necessarily just the integral test. So it's just how the problem was phrased or the specific series is given. That's why we are probably having troubles using the other tests. So upon simplification, this will just be n squared of ln of n plus 1 all over n plus 1 squared ln n as n approaches infinity. And then here, to get the limit, I might need to use the L'Hopital's rule or the version of L'Hopital's rule. So because this would be infinity over infinity, right? So I can try L'Hopital's. So derivative of the top would be obtained by using the product rule. So it's going to be n squared over n plus 1 plus 2n ln of n plus 1. And this doesn't look good. So I'll have n plus 1 quantity squared over n plus 2 times n plus 1 times ln n. I'm not seeing where this would lead us. I'm thinking probably is the integral test the last resort here? Okay, let me think a bit. Yeah, I guess we don't have a choice but to use the integral test for this guy because all the other tests fail. So yeah, exactly, Herson. Because there might be some tricks that I need to use in order to evaluate this limit because it doesn't look good. But the thing about the integral test, if I'm right, for the integral test, you need to take the improper integral of this guy. Perhaps you will need to use integration by parts. Because U substitution will not work, and you will need integration by parts. But let me see. But this would be convergent. Yeah, you can use the integral test here. Take the improper integral from 3 to positive infinity, or you can start at 2. If that's the original problem, over n squared dn. Here you'll need to use integration by parts. Yeah, but you will that improper integral will be finite, I guess. If we start at 2, let me do a quick calculation. I think it would be, the integral would be ln 2 plus 1 all over 2, which is finite. So here, use integral test. That will require integration by parts. So yeah, unfortunately we used up all our time for today, but so I won't be able to finish the solution integration by parts. But yeah, I think you will be using integration by parts to evaluate it. You can use u to be ln x, and then dv is x to the negative 2. Yeah, I hope so too, that you won't see this in the exam. But you see that all the test fails, actually, or you will eventually get this limit, but I guess the limit will be equal to 1. My guess, but don't count me in that, or don't hold me to that. I think this limit will be equal to 1, so the ratio test will be inconclusive, essentially. So you'll be really needing the integral test for this one, okay? But I hope these examples, so this is convergent, gave you sort of an idea of how to work out problems about absolute convergence and conditional convergence. Okay, so on Monday, let's go to power series and probably Taylor series expansions as well. All right, guys. So I think that's it for now. So see you again on Monday. Have a good weekend, everybody. Bye, guys.